This is a motor, one of the most important electrical components. It allows us to turn electrical energy into mechanical energy.
We've all learned about it and understood how it works, but this year we were tested to build one from scratch.
To begin, we isolated all of the most important parts of the motor.
First up, there's the stator, which acts as a casing of the motor and holds the magnets on either side of the rotor, which is the part of the motor that turns.
A shaft goes through the rotor and holds the coil windings responsible for carrying electrical current through the motor.
Next, there's the commutator, which is a ring that is separated into different parts that connects to the ends of the coils that allow the creation of a circuit with the help of brushes.
These brushes are connected to the terminals and brush against the commutator to allow electricity to flow through the coils, thus completing the circuit. The terminals allow connection to the battery, which powers the motor. During the term, we actually made 2 motors. However, the first one was an unsuccessful attempt, since our commutator was not properly connected, and 2 coils were not strong enough. In this video, we will be talking about the successful attempt.
For the body, we used a metal straw as our shaft, with 2 MDF rings that had screws going through them to hold the winding. In order to ensure that the rings were properly centered onto the shaft, we thickened the straw using some tape. It's important that the shaft is centered properly, as it would affect the way the motor spins and it would wobble. This affects the amount of work the motor can do.
After the body was made, I worked on the armature. This motor had 4 coils, which means that it would be self-starting as well. We used copper wire for our coils. I coiled the 2 coils parallel to each other first and flagged them so I would know how to connect them later on. And then I coiled the last 2 coils perpendicular to the first 2.
The commutator went through the most changes. At first, we used an aluminum soft drink can, since it was naturally rounded and easy to cut. To ensure that the commutator was perfectly rounded, we used a thick straw and placed the commutators around it in order to ensure that the brushes wouldn't lose connection with the commutators as the motor spun.
However, this didn't work because aluminum oxidizes really quickly, and it wasn't pure either since it was from a drink can. Along with that, when we tested its resistance with a multimeter, it was way too high.
The straw was also unstable and did not round the commutators enough.
Next, we decided to use galvanized iron sheets, which were way more conductive due to the zinc coating. While these would also wear down faster, it was way more conductive and had a lower resistance.
Mr. Thomas 3D printed a small piece which held the commutator sheets from the top. To make it more stable, we also fastened a zip tie to the bottom to keep the sheets rounded and in place. We also wanted to keep a gap to ensure that the commutators weren't touching.
The ends of the copper wire were soldered onto the commutators to ensure a good connection. Lastly, we tested to ensure that there was continuity between the opposite commutators, since the brushes would be touching there and would power very specific coils.
For the stator, we began by using metal brackets which would hold the 2 magnets with the opposite poles facing each other to create a concentrated magnetic field around the wire. We also used bearings at the ends of the body to make it easier for the motor to spin, since we wanted to reduce the amount of work the motor had to do in order to overcome friction.
Later on, we swapped the brackets for a 3D printed shell that Mr. Thomas printed to make the whole motor look more polished.
Lastly, we tried using carbon brushes for the motor originally, but ended up using a thick wire that was stripped, since it had a larger surface area and made contact with our commutators better.
This whole project really taught both of us a lot about resilience and creativity, since we constantly had to change components on our project for it to work.
We had many failed attempts, but it was those attempts that gave us the most information for improvements. During this project, I was incapacitated physically as I had broken my hand, so being able to work together on this had its challenges, as while I had better knowledge on certain aspects of the project, I was unable to do them myself, instead having to resort to explaining it to Nahl.
Both of us aspire to work as engineers in the future, and hands-on experiences like this are invaluable to students like us, since it gives us the much-needed experience in the field.
It also allows us to actually apply our theoretical knowledge in the physical world, and cements our scientific understanding outside the classroom.